NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a system of quadratic equations exactly following a clean step-by-step structure. Here is the example we will solve. Step 1. Subtract the second equation from the first to eliminate the constants on the right. Then factor the result carefully. Step 2. Use the zero product property. Either x minus y equals 0, which means x equals y, or x plus y minus 1 equals 0, which means x equals 1 minus y. Now solve case 1, x equals y. Substitute into the first equation and factor. This yields x equals 3 or x equals negative 4. And because x equals y, we get the ordered pairs 3, 3 and negative 4, negative 4. Now solve case 2, x equals 1 minus y. Substitute into the second equation. Solve the quadratic in y using the quadratic formula. Then compute x equals 1. Then compute x equals 1 minus y to get the matching ordered pairs. To summarize, the complete solution set contains 4 ordered pairs. Example: we will solve a system of quadratic equations following a precise, step-by-step algorithm that matches the provided solution outline. The system is x minus y squared equals 3, and x squared plus y to the fourth equals 13. Step 1. Start from x minus y squared equals 3. Square both sides to get parentheses x minus y squared, all squared, equals 3 squared. Expand the left side, x squared minus 2x, y squared plus y to the fourth equals 9. Step 2. Group the terms as left parenthesis x squared plus y to the fourth right parenthesis minus 2x y squared equals 9. From the system, we also have x squared plus y to the fourth equals 13. Substitute 13 for that group to get 13 minus 2x y squared equals 9. Therefore, x y squared equals 2. Step 3. Solve for y squared. Y squared equals 2 over x. Step 4. Substitute y squared equals 2 over x into x minus y squared equals 3. This gives x minus 2 over x equals 3. Step 5. Multiply both sides by x to clear the denominator x squared minus 2 equals 3x. Move all terms to one side, x squared minus 3x minus 2 equals 0. Step 6. Use the quadratic formula to find x equals open parenthesis 3 plus or minus the square root of 17 close parenthesis over 2. Step 7. Because y squared equals 2 over x must be non-negative, x must be strictly positive. The value 3 minus square root of 17 over 2 is negative, so it is not acceptable. Therefore, the valid x is 3 plus square root of 17 over 2. Optional final note: if we also want y, substitute the accepted x into y squared equals 2 over x to get y squared equals parenthesis square root of 17 minus 3 close parenthesis over 2. Thus, y equals plus or minus the square root of that value. In this lesson, we will solve a symmetric system and find x, y, and z in terms of a and b. We will also state conditions for real, distinct, and positive solutions. Here is the system. First, x plus y plus z equals a. Second, x squared plus y squared plus z squared equals b squared. Third, xy equals z squared. Step 1. Square the first equation and use the identity. The sum squared equals the sum of squares plus 2 times the pairwise products. Step 2. Replace xy by z squared. Then factor z and use x plus y plus z equals a to solve for z. Step 3. Use the first equation to get x plus y by subtracting z from a. Step 4. Treat x and y as the two roots of a quadratic with sum and product known. The variable u stands for x or y. Step 5. Apply the quadratic formula. Notice the symmetric plus-minus pair gives x and y. Finally, conditions. For real and distinct x and y, the discriminant must be positive and a must be non-zero. That is left parenthesis 3 a squared minus b squared right parenthesis times left parenthesis 3 b squared minus a squared right parenthesis greater than 0 and a not equal to 0. For positivity of z, the fraction a squared minus b squared over 2 must be positive. One convenient branch is a greater than 0 and a squared greater than b squared, which also makes x and y positive when the discriminant is positive. Recap. Expand the sum, substitute the given relations, solve for z, then form a quadratic to get x and y. Check the discriminant and signs to ensure the required solution type. We will solve a non-symmetric system involving square roots, step by step, exactly following the algebraic structure shown on screen. Here is the system we will solve. First, x minus y equals 5. And second, the square root of x plus the square root of y equals 5. We begin with x minus y equals 5. Now recognize that x minus y can be written as the quantity square root of x minus square root of y times the quantity square root of x plus square root of y. Since the sum of the square roots equals 5, substitute that directly. Divide both sides by 5 to isolate the difference of the square roots. Now we have a new two-equation system in the square roots. Add the two equations to eliminate the negative term and solve for the square root of x. Then back substitute to get the square root of y. Finally, square both results to find x and y. If the square root of x is 3, then x equals 9. If the square root of y is 2, then y equals 4. Check quickly. 9 minus 4 equals 5, and 3 plus 2 equals 5, both true. Therefore, the solution is x equals 9 and y equals 4. In this lesson, we will solve a non-symmetric system and find x squared. Here is the system. The product x times y cubed equals a to the fourth, and x cubed times y equals b to the fourth. We are asked to compute x squared. Step 1 of the algorithm is to multiply the two relations. Multiplying left sides and right sides gives x to the fourth times y to the fourth equals a to the fourth b to the fourth. Taking the principal square root of both sides, we get x squared y squared equals a squared b squared. Step 2 is to divide the two relations. Dividing the first by the second yields y squared over x squared equals a to the fourth over b to the fourth. Therefore, y squared equals a to the fourth over b to the fourth times x squared. Step 3. Substitute our expression for y squared into the result of step 1. Replace y squared by a to the fourth over b to the fourth times x squared. This gives a to the fourth over b to the fourth times x to the fourth equals a squared b squared. Solving, x to the fourth equals b to the sixth over a squared. So x squared equals the absolute value of b cubed over a. We take absolute value because x squared is non-negative and is the square root of x to the fourth. For completeness, we can also express y squared. Using y squared equals a to the fourth over b to the fourth times x squared, we get y squared equals the absolute value of a cubed over b. A quick check shows both original equations are satisfied in magnitude. Final answer x squared equals the absolute value of b cubed over a. In this lesson, we will solve a classic non-symmetric system involving powers and a product constraint. We'll go step by step, turning the system into a simple quadratic in x to the power n. Here is our system. The first equation is a times x to the n plus b times y to the n equals c. The second equation says x times y equals k, with k not equal to 0. Step 1. From the product condition x times y equals k, solve for y. Since k is non-zero and x must also be non-zero, we can write y equals k divided by x. Step 2. Substitute y equals k over x into the first equation. That gives a times x to the n plus b times the quantity k over x to the n equals c. Step 3. Simplify the power of a quotient. The quantity k over x to the n equals k to the n divided by x to the n. Step 4. Clear the denominator by multiplying every term by x to the n. We obtain a times x to the 2n plus b times k to the n equals c times x to the n. Step 5. Move all terms to one side to write a clean polynomial equation in x to the n. Step 6. Solve the quadratic in t using the quadratic formula. T equals c plus or minus the square root of c squared minus 4, a bk to the n all over 2a. Step 7. Take the nth root to recover x. For each admissible branch, x equals the nth root of that expression. Then use y equals k over x to get y. So the system reduces to a quadratic in x to the n. Solving that gives us all possible x values. And then y equals k over x completes the solution set. In this lesson, we will analyze a system with a parameter and find for which values of the parameter the system has real solutions. Here is the system. Our goal is, for which values of a does this system have at least one real solution pair x and y. First, isolate y from the second equation. From x times y equals a, we get y equals a over x, provided x is not 0. We'll handle x equals 0 implicitly by the algebra that follows. Now substitute y equals a over x into the first equation. That gives 4x squared plus the quantity a over x squared equals 8. Clear the denominator by multiplying both sides by x squared. We obtain 4x to the fourth minus 8x squared plus a squared equals 0. This is a biquadratic equation. Let t equal x squared. Then the equation becomes 4t squared minus 8t plus a squared equals 0, a quadratic in t. For the original system to have real solutions, the quadratic in t must have at least one real solution with t equal to x squared. So t is non-negative. A necessary condition is that the discriminant is non-negative. The discriminant is negative 8 squared minus 4 times a squared. That must be greater than or equal to 0. Simplify the inequality. We get 64 minus 16 a squared greater than or equal to 0. Therefore, a squared is less than or equal to 4. So the parameter a must satisfy the absolute value of a is at most 2. Visually, all allowed values of a lie on the closed interval from -2 to +2. Conclusion: the system has real solutions if and only if the absolute value of a is less than or equal to 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.